Today we begin your first calculus topic. Big smiley face for that. We are now into calculus. Your days of being a pre-calculus student are over. So when we talk about this concept of a limit, which is very foundational in the whole world of calculus, we first have to go back to this idea of what we talked about last year over and over again, and that is the idea of what does f of x really mean? Okay? When we talk about this idea of f of x, I know that that's kind of the name of a function, but we need to really ingrain in our mind this idea of function values. And function values really are just the y values. Okay? So if I were to look at this function, if I were to put some labels in here, okay, just like that. There's some labels. Then, and if I were to move along this function, what is the function value right here? 1. And as I keep moving along the function, what is happening to the function value? It's increasing. So by the time I get to here, what's the function value? Right here. The function value here is 3. And the function value keeps going up, all right, on this particular graph that I've shown. As I move this way, what is happening to the function value? Decreasing. What's the function value right here? 0. And then when I keep going, what's happening to, what are the function values now? Are they positive or negative? So over here, the function values are negative. Over here, the function values are positive. But all of this is happening. Remember the function machine? Aren't there two pieces to a function? You put in an x, all right? You put an x in to the function machine, whatever that is, and you get out a y. So all of this is related to x values. So we could say as these x's are increasing, okay, as the x's are increasing, on this particular function, the y's are increasing. As I move from left to right, okay, I could even say as this x approaches, what if I had some hash marks in here? As x approaches 4, the y value approaches 3. Would you agree with that? And I could come back this way, and I could say as x approaches -2, the function approaches what? 0. So this idea of function values is critical, all right? And that leads us to this note. In calculus, we are often interested in what a function approaches as we get really close to a certain x. Okay? And I could have added up there in what value. Let's add that in. In what value a function approaches as we get really close to a certain x. Now, I want to bring up this little phrase that you're going to hear me use a lot. Verbally nag. Sounds like a negative term, like something an old mean wife does to her husband. But that's not what we're talking about. What we're talking about is an approach to a lot of our calculus problems this year, and this is very important with the people at the College Board who, they're the ones that design the AP tests. We're going to look at things verbally, which means we need to be able to explain things, okay? We need to be able to explain things. We're going to look at things numerically. And when we think about numerically, we can think, an example of that would be the table of the TI-84. Okay, that would be an example of looking at things numerically. We'll look at things analytically. What do you think that is? Algebraically, okay? That's where we actually work through the algebraic steps to explain something. And then, so what do you think the G stands for? Graphically. We have to be able to work in all four areas. We have to be able to explain what we're talking about. And then we have to be able to justify what we're talking about using numerical explanations, analytic explanations, and graphical explanations. Not on every single problem, but we have to be able to do all of those things because the College Board, when it comes time for the AP test, that's one of the things they check on. Can you use all of those techniques? So, with that in mind, let's look at a function here. X cubed minus 2x squared over 3x minus 6. Let's plug this function into the graphing calculator. So we have x cubed minus 2x squared on top, and it's divided by, in parentheses, 3x minus 6. Okay? And, we can, of course, look at the graph of this thing. I'll go zoom standard. It kind of looks like a parabola, doesn't it? Right? So, it does look like a parabola. I'm just going to paste this in case I want to draw on it. Okay, it looks like a parabola. But let's do something here. Let's go to some table values, shall we? Let's go to my table setup. And I want to start at 1.995. And let's go up. Let's make my delta table 0.0001. All right? And then let's go to my table. Now, as we scroll down, and I get really close to 2, I want you to notice what's happening with my y values. But aren't they approaching, aren't they staying very close to one another? Doesn't it look like they're approaching 1.33? right? And when we get to 2, there's an error. Good job. I heard somebody say that. There's an error. Why is there an error? Look at my function. Why is there an error? We've talked about this. Because, good, this is a rational function. And if I look at this thing, I cannot have a 0 in the denominator. So when x is equal to 2, I get a frowny face, undefined situation. All right? So right at 2, if I were to draw this graph correctly, here's 1, here's 2, there would be a hole here. Okay, and that's kind of small. Let me draw it a little bit bigger. There would be a hole. So here at 2, there is a hole. But we just looked at some table values. What does this function as we get close to 2? By the way, let's go back to my table and let's see if the same thing is happening as we go past 2. Yep. So if we look at, I want to get that error right in the middle. Sorry. As we look at this table, all right, isn't it safe to say that as x gets really close to 2, okay, as we get really close to 2, I need a color, from both directions, what is the function value approaching? Don't look right at 2. Look as we get really close to 2. Isn't it 1.33 approximately? All right. So in this case, as we approach 2 from the left and as we approach 2 from the right, the function value is approaching 1.33. Even though it's not defined right at 2, we could say that this function is approaching the value of 1.33. And what we have just done is done a good graphical and numerical explanation of our first limit. We could make this statement. We could say the limit of that and by the way, we put LIM for limit. We could say the limit of x cubed minus 2x squared over 3x minus 6, the function we were working with. I could say the limit of that function as x approaches 2, all right, is 1.33. And I'm going to put the little approximately symbol up there. Now, how did we just look at that? We looked at it both numerically and graphically. All right, we have not looked at it yet analytically. Let's do that. Let's look at this thing analytically. If I have, let's start with my function, x cubed minus 2x squared over 3x minus 6. Okay? Now, do you see something I can factor out of the top? More than that, an x squared, right? I can factor out an x squared, and if I do that, I'm left with x minus 2. On the bottom, what can I factor out? A 3, and I'm left with an x minus 2. Get out the slasher. And look what I'm left with. I'm left with f of x equals 1/3 x squared, or x squared over 3. right? Now let's find f of 2. Weren't we looking at 2, right? What happens now if I find f of 2? 1/3 times 2 squared. Isn't that equal to 4/3? Right? And what is 4/3 as a decimal? I bet I know. 1.33 repeating. That is the analytic argument for this statement up here, for saying that the limit of that function, all right, as we get really close to 2, now not all the way to 2, okay, because at 2 it's undefined, right? At 2 there's an error. But as we get really close to 2, okay, as we get really close to 2, this function gets really close to 1.33. And that is the first concept of a limit. So, let me see here. We have a statement now that we can kind of finish up this first day with. As x gets closer to a, but x cannot be equal to a, does the function value get close to some real number L? Okay, and that is a very important question for limits. And then our second question is probably more basic. Okay, and I'm just going to phrase it this way. Can we get close enough to A? All right. Obviously, sometimes there could be a number of values that are not defined. Okay? So L is our y value that we're approaching. Like the one we just did, that was the one we just did, it was 1.33. Okay? That was our value L. All right? So if the answer to these are yes, if yes, then we would say the limit as x approaches a of whatever our function is equal to L. And that is the introduction to limits, day 1.